What I want to do next is generate a set of parametric equations that will generate what I refer to as the cycloid. I can't do it, can I? My goodness. I think I can spell cycloid. So everybody, here I go. I want you to imagine that I've got a circle which actually is a wheel. And I want its center to be located on the y-axis, and it's just resting on the x-axis. And I want you to put a red ink marker right there on that part of the circle. And keep it that part of the circle, and then roll the circle down the x-axis. I think what we're going to generate is a curve that is something like this. I'm trying to avoid my red pen. It's hard to see. And I do think here's orientation. So unlike my first couple of silly examples, let's see if you and I can actually dive in here and generate this set of parametric equations that describes this whole new curve from thin air. So allow me to roll that wheel, roll that circle down the x-axis just a little bit. The cycloid looks like this, and I'm going to consider an arbitrary point on the cycloid that does this. Now, with this particular point of interest, notice how if I were to take a break and identify the location of the center of the circle, for whatever reason I might have, notice how as I roll this wheel, the circle down the x-axis, the vertical position of the center doesn't change. And I think that the y-coordinate, therefore, the center, no matter where this circle is going to be nothing more than the radius of the circle in question. Can I call it A instead of R? A is just a constant, it's the radius of the circle in question. Now, as far as the x-coordinate of the center, okay, I'll use a little bit of red. I think the x-coordinate is nothing more than this length in red on the x-axis. But if you roll the circle back in such a way that the center's on the y-axis again, that length of this, should I say, the length of this red line segment on the x-axis is the same as the length of this portion of the curve. The curve is a circle, though. And so when it comes to that length, it's just arc length. And recall from trigonometry, the length of an arc S is nothing more than the product of its radius times the measure of central angle theta. Now, my pretty picture, let me connect the center to that point P, drop a vertical, drop a horizontal, got a nifty little right triangle. And all I'm suggesting then is this. If I treat this as my parameter T, I like it up there, not over here, because when I roll the circle back in such a way that the center's on the y-axis, T is going to be 0. That's why I chose that angle to be T, not the other acute angle. Notice then that the length of this arc is just the radius of circle A times the measure of central angle theta, or in this case T. And so changing theta to T so I can use my familiar parameter T instead of theta. The center's x-coordinate is this. So AT comma A. Now that being the case, notice that the x-coordinate of the point P, the coordinate of that point right there, is nothing more than the x-coordinate of the circle minus that length right there, which is just a horizontal leg of that right triangle. So in other words, what I'm really suggesting is this, that it can be interpreted as the x-coordinate of the center of the circle. So x-coordinate of the, I didn't say center, did I? My goodness. Which is nothing more than this, minus the horizontal leg of that nifty little right triangle. But remember, the radius is A. So A is also the hypotenuse of that right triangle. Doesn't that mean necessarily that this horizontal leg divided by A is equal to the sine of T? And so I think the horizontal side is going to be nothing more than A times the sine of T. Now I think likewise, why it can be interpreted as nothing more than, well, let's see, this vertical distance could be interpreted as the y-coordinate center minus the vertical leg of the right triangle. And so I think I can represent y as, let's see, the y coordinate of the center is just as constant, minus the length of the vertical leg of the nifty little right triangle, but certainly the cosine of t is going to be horizontal leg over hypotenuse. Cosine of t is going to be horizontal. Cosine of t is going to be the length of the vertical leg over a, but that basically implies that that vertical height, the length of vertical leg of that right triangle is a times the cosine of t. So I think out of thin air, I just happen to have generated a set of parametric equations that describes that interesting curve that I had drawn on the other side of the inkboard. Now, this would be a really good example to go through in terms of some calculus on parametric curves. Unfortunately, the author of the text stole the wind out of that. So he actually dives into exactly this set of parametric equations to look at some calculus tools. So if you don't mind, I'll leave that for you to read, and I'll make up different examples, as I typically do, of course.